Hello everyone. I hope I am live now. So those who are watching me live, can you guys give me the confirmation that am I visible or not? I hope you all are doing well. So you already have watched from my thumbnail as well as from my heading itself that today's objective is to talk about binary search tree. So yesterday or a few days back only, I was exploring my playlist of DSA using Python, and I have seen that the concept of binary search tree is missing, which is really important to understand for everyone. So that's why I thought that why not to take it live, and if you have any sort of questions, you can ask me on the go itself. That's the beauty about taking the live sessions. So today we will try to discuss more about the binary search tree itself. I'll start with the fundamentals of BST, followed by what are the operations that we usually do and how we can do. I'll do the implementation as well. And further, if time permits, we'll try to discuss the interview questions also. So it's a very full-fledged session regarding the binary search tree. But before I'll start, can you guys give me the confirmation in the chat window that whether I am clearly visible, clearly audible or not? I'm waiting for the confirmation. If someone will give to me, it would be really helpful for me to get the understanding that my voice is clearly audible or not. Is this clear? Can you guys give me the confirmation? And then maybe I'll start sharing my screen, and within a few minutes, we will start the session. So I got the confirmation from Pravi that it's audible. Thank you so much, Pravi, for the confirmation. Now, what I will do is I'll try to share my screen, and you guys will confirm to me that whether my screen is also visible or not. Okay. Perfect. Is my screen is visible to everyone? सबको screen दिख रहा है? Is my screen is visible? Can you guys give me the confirmation? Yes or no? I hope one YouTube screen is coming up, right? Okay, perfect. Perfect. So now, those who will not able to join me live, the video will be saved in a playlist of DSA using Python. I'm showing you in the very starting of the session so that if there is anyone who want to watch it again, the recorded part to revise the session. So if you will observe, this is a complete playlist which you can refer to understand the concepts of data structure and algorithms. Here, if you will observe, if you will go below, after the discussion of tree traversal algorithms, let me just check it out. Yes. After the discussion of this tree traversal algorithm, which is in order, pre-order and post-order, you will be able to observe that we will be having the today's live session which is going on, which is about understanding BST, real applications and top interview questions explained live, right? So this is the today's session which I'll store it in this particular playlist. So in future, if you want to refer the concept again, maybe for the revision purpose, maybe to go for before going to the interviews, you want to revise the concept, so you can check it out here. I hope it is clear to everyone. Now let's get started without any further ado regarding the concept of binary search tree. So Joan is saying, glad to see you back after a long time. Please be consistent. I think my videos keep on coming up, right? So after 1 or 2 days, I used to upload the videos. So either the recording will come. If sometime recording will not come, so I'll try to come up live a lot in that particular week. So I am consistent on YouTube, but the thing is that the recorded part is coming up as of now, right? So here now, let's get started with the concepts of binary search tree. So here, BST. Now, before we will start, let me give you that idea of the prerequisite to understand today's session. Who all will be able to enjoy this session? Who all will be able to properly understand this session? The very first thing, as I told you in this YouTube playlist itself, if you will observe, I have mentioned everything in series. So you should be aware about the tree data structure. So if there is anyone who is not having a good understanding about a binary tree, I'll start from a scratch, but still, if you have an idea, that would be a good thing. And on top of that, if you have an idea about pre-traversal algorithms, which we have in order, pre-order, and post-order, these three traversal algorithms also you know pretty well that how it works. Okay, so I'll not explain those things which I already have explained on my channel because that's of no use, right? I want to give you new and fresh content so that you can also enjoy that content, right? So that thing we already have covered up. So if there is someone who is not having an idea about those traversal algorithms, you can refer that playlist and check it out, that video as well. Moving ahead, the next important thing is that you should be comfortable with the Python programming language because I'll do the implementation in Python on the lead code based platform itself directly. Okay. If you want to do the implementation in any other programming language, you can do, right? If you know the concept, as I always say that this concept, this particular DSA is independent of any programming language. Once you understood the concept, you can do it maybe on your own language also, right? So let's get started with the concept of binary search tree. Before moving ahead with the binary search tree, you should know what this binary tree is all about. And let's start with the before binary tree, let's start with what is tree data structure. Who will help me to understand what is the meaning of a tree data structure? Anyone who can let me know? So if you remember in the very start of the session, when this playlist started, when I explained you the concept of what is data structure, I explained to you that data structure is a way to store the data in a proper organized manner. And at that point of time, I explained to you that data structure is of two types. Anyone knows that? I told you that DS data structure is of two types. Yes. One is, so as Subhash said, it's a non-linear based data structure. So one is a kind of a data structure which you will observe is of linear type, right? And another one is of a non-linear type. Non-linear type. So when I'm saying linear based data structure, we have already discussed in our playlist about arrays, right? In a very great depth. We have discussed about linked list. We have discussed about stack and queues, right? All these are the examples of something called as a linear based data structure. When I'm saying non-linear, the concept of trees that we are discussing today, the concept of graphs, which I already have discussed in my playlist, all these concepts are coming under the category of a non-linear based data structure. Fine. Now we get to know that tree is a non-linear based data structure. Acha, if I'll ask you one simple question, what is the difference between trees and graphs? If both of them are non-linear, then what is the major difference between the trees and graphs? Who will tell me? I think this is what I have already covered up in one of my video. Still, who will tell me what is the difference? If someone will ask you in an interview that, can you tell me what is the major difference between the trees and the graphs? Anyone who can have the answer? So I usually say one statement which clearly explains this thing. I usually say that every tree is a very good. So I already got the answer. This is what I was looking for. That's why I was making it very slow line. So graph can be cyclic. That's the only ultimate difference if you will observe. So if you will observe, when you're talking about a graph, you can say that graph is a bigger picture. In terms of visualization, if I have to show you, so graph is a bigger picture. So in graph, we can have cycle as well, or it can be acyclic as well, right? It can be acyclic as well. Tree is a component, or you can say is a subset of that graph. Okay? Tree is a component. So here, when I'm saying tree is strict portion, which says that I'm always be acyclic. I'm always be acyclic. Okay? So now let's move ahead towards the concept of in trees. Now we are moving ahead towards the concept of something called as binary tree. So step by step we will move towards BST. So what is binary tree? First of all, let's try to understand this. Who will tell me what is the meaning of a binary tree? Name itself is saying the definition. Binary. Binary. So what is the meaning of a binary tree? Anyone who can give me the result, who can give me the answer? Try to be more interactive in the session, then only you will also be able to enjoy the session, and then only I will be also able to enjoy the teaching with you all. So please be more interactive and try to give the answers as soon as possible in the chat window, right? So what is the meaning of a binary tree? Very good. So as Vikas already said, that at most two child nodes will be required, right? So it says that ज़्यादा से ज़्यादा, binary tree means ज़्यादा से ज़्यादा दो child nodes होंगे. It will be having at most two child nodes. So this is a very crucial word to understand. Any tree which is having at most two child nodes will come under the category of a binary tree. Fine. So either it can have zero node, which is something which we call as a leaf node in a tree, or it can have one node, or it can have two child nodes, right? This is what we call as binary tree. Now let's move in more depth now towards the binary search tree. Binary search tree. By the way, I'll attach all the notes and will give you all the notes whatever I'm mentioning in the code files also. So just you just have to focus on the session itself. Everything will be given to you in the comment of this video, as well as I'll try to attach in the LinkedIn post as well. Okay, so just don't worry about the notes and all stuff. Fine. So let's move ahead with respect to BST. What is binary search tree? Now, again, it's a component in binary tree itself, but here one another word is coming up, search, right? So binary search tree is again more stricter version of a binary tree, where that property will retain same, that it can have at most two child nodes because it's again a binary tree, but it's a BST, binary search tree. So the constraints are, it says that the very first constraint is that the nodes which are smaller than the parent node will always be present at the left side. So left subtree, left subtree will always contains that data which is less than the, strictly lesser than the parent node data. Parent node data. Similarly, it says, okay, there is something which Vikas said which is wrong. This is wrong. So I'll rectify this because many people usually say this statement only. So I'll come to this point, but let's move ahead. Right subtree will always contain the data which is bigger than the parent node data. So this is the stricter version of a BST. It says that, let's say you will be having data points. So you have to arrange those data points in a way that always your left subtree will contain the values which is smaller than the parent node data. Right subtree will contain the values which is bigger than the parent data. So let me give you one simple example with the help of which everything you will be able to understand. Now, let's say we will be having 100. So 100 is the first node. Please focus here and please try to be with me until the end of the live session. Then only you will be able to get the beautiful insights about this session, right? So 100 is the root node because it's the very first node. Now, the next value is something which we have is, let's say, 80. Now tell me where this 80 will be inserted. Because this next particular element is having a value which is less than 100. I'll compare this with the root node. So I'll try to allocate this or insert this at left of 100. This is how basically the insertion will happen in binary search tree. This is how you will be able to learn how the insertion is happening. Again, let's say the element is 120. So where it will be allocated? It will be allocated towards the, because again, you always start from a root node. Now you will start comparing that this element is smaller or bigger. Because 120 is bigger than the root node, so I will move towards the right and will allocate this that 120 towards the right side of a 100, right? Everyone is saying it correctly. That's superb. It means you will be able to get the point which I'm trying to convey here. Let's move ahead. Let's say we will be having an element like 50. So where this 50 will be allocated? Where this 50 will be allocated? Let me know. Who will tell me? Just be fast. Where this 50 will be allocated? I want 100% energy in this session. Okay. So where this 50 will be there? So again, you have to start from a root node. Start directly from the root node. 100 will be there. Very good. So as Subhash and Vikas has said, already said, it should be always at the left of 80. Why? We start from 100. 50 is smaller than 100. We'll go towards the left side. 80 is there. 50 is smaller than 80. So I'll go towards the left and will allocate 50 here. Let's move ahead to the next important value. Maybe let's say I want to allocate 95. Where 95 should be allocated? Where 95 should be there? So again, start from 100. 95 is smaller. Go below. 80 is there. Again, 95 is bigger, right? So you have to go towards the right side of 80. Let's say next element is 135. You will start from 100, then you will go towards 120. Because 135 is bigger than 120, you will go towards the right side of 120 and insert 135 there. Again, let's say you will be having a value like 110. You will start from 100. Next element is 120. You will go towards left side of 120 and store 110 there. This is how basically a complete binary search tree is created. Binary search tree is created. This is something which you will call it as a BST, where if you will observe, at every point of time, the root node or the parent value is compared. And if you will observe, left subtree or left node will always have a smaller value and right subtree will always have a bigger value. Now, why I said in the initial part of the session that the answer which is given by Vikas is incorrect, he said left is lesser or equal to right. There is nothing term as equal to here. So BST says that we will be not entertaining any duplicate elements in the tree. There will be no duplicates. As John already said, there will be no duplicates, right? There will be no duplicates in the original BST, but still there are few definitions in the websites where you will feel like that they're taking the duplicates. So they're manipulating the things. But if you will go to the standard things, standard books, they says that there will be no duplicates. We will be able to entertain in a binary search tree. Always remember that. Okay. So there will be no equal symbol. Is this fine? Now, let's move ahead. Let's move ahead to the next important part. Is this part is clear? So this is what the fundamental property of binary search tree I have talked about. Property number 1, property number 2. And according to that property, we have tried to create one BST, which is a valid BST. Is this clear to everyone? Shall we move ahead to the property number 3, which is very, very important and which will really help you to solve so many top-notch interview questions in the companies. Shall we move ahead to the next property, if everyone will allow me? So far, so good. Can I get some thumbs up or something like that so that I will get to know that so far, so good, everything is clear? Any confirmation will I be able to get from everyone? So until so far, we are understanding what is BST. Okay. So in this, we have talked about property number 1, that left subtree will be having a smaller value than the parent node. Property number 2, right subtree will be having a bigger value than the parent node. Let's move on to the property number 3. So I got the confirmation from many people that it's going so far so good. Let's move ahead. So property number 3 says, if you will do the in order traversal of a tree, if you will do the in order traversal of a binary search tree, At that point of time, let's try to do that without if I'll say to you, you will cram it, right? Let's try to do that. So we will be having above example as a valid BST. Can anyone give me the answer? What is the in order traversal of this particular tree which I have just now created? What is the in order traversal of this tree? Yes, in order traversal means, as I already said, it's the prerequisite to understand that what is this. So let me tell you, it's something which says that first of all, you have to recursively explore towards the left subtree. Okay. Then you will move recursively. Then you will try to display that root dot val, or you can try to store it as well, depending upon the circumstances, the problem statement. And then you will explore towards the right subtree recursively. So by doing this, let me know what is the answer of a in order traversal you will be able to get. So yes, the answer should be, it will be nothing but is equals to, so go towards left subtree, then in there also left. So you will be able to get 50, then root is 80, then 95, then bigger root is 100, then 110, then 120, then 135. So I am not going in a lot more depth. Again, always remember, so as I said you, the prerequisite of this session, the very first thing is, as I told you, you should be aware about the tree data structure, although I have given you a brief overview. Second thing is, you should be good with the tree traversal algorithms. Okay. Third thing is, you will be only able to understand this tree if you know the concept of recursion. Already I have made the videos on recursion as well. So these things plays a very important role in order to understand the today's session pretty well, right? Everything, almost everything in trees, you will be able to solve almost every question via recursion because it's very easy to implement, right? So now here, if you will observe, when you will do the in order traversal, what you are getting, have you observed this? You are getting something called as a sorted array. What is the meaning of a sorted array? The array is arranged in a ascending order, right? So there's an arrangement going on, and that too in a ascending order. Yes or no? Have you observed this? So always remember, the property number 3 says that at any point of time, whenever you will do the in order traversal of a BST, you will always get a sorted array in the form of a ascending order. Always and always, right? 100% guarantee is there. If let's say in an interview someone will ask you this question, even on the lead code also there is a question by the name of a validate BST. If I'll show you this question. So let me show you this question. Here, if you will see, validate BST. This is a very widely asked question in a lot many companies. So what this question says that let's say we will provide you one tree. Now we are not sure that whether it's a valid BST or not. Can you tell me? So one good alternative is, first thing is, you can just try to check the properties at every point of time. Is the left subtree is having a value less than the root value, or right subtree is having a value bigger than the parent node? Second, another interesting way is that what you will do is, for a given tree, you will try to do the in order traversal and then check it out that whether that in order traversal of a tree is sorted or not. If it's sorted in an ascending order, you are 100% sure that tree is a BST. Otherwise, that tree is not a binary search tree. Is this part is clear to everyone? So how is this properties helping you to solve that question? Is this clear to everyone? Even there is another interesting question to find out the kth smallest element in a BST. In this question also, you will be able to apply the same important property of this property number 3 to get the kth smallest element in a BST. For example, if I'll say, in this given tree, can you give me the third smallest element? What you will do? You will do one simple thing. You will say that I'll do the in order traversal, and after that, I know that the array will be arranged in a sorted manner in ascending order. So if let's say I'll store it in my array. If let's say if I am looking for a third smallest element, If a user is saying that, can you give me k as 3, means can you provide me the third smallest element in a given array, in a given tree, in a given BST. So what you will do? You will just check out that result array where you have stored your data in the ascending order. You will say, what is the index number you will be able to pick? You will be able to pick the index number as 2, which is nothing but k minus 1. Whatever be the value of k is there, you will say that I'll pick up the value of k minus 1, because that is the index number which will be giving me the kth smallest element in a given array. Yes or no? Is this easy or difficult? Will you be able to understand what I'm trying to convey here? So far, so good. Maybe what I can do here, I'll try to implement out of these two questions a single question, and another question you can take it as an assignment, which you can do at your home. Okay. Let me try to do the implementation of this kth smallest element. Again, if you will observe the same problem statement, they are saying the root of a BST is given, integer k is given. You have to fetch the kth smallest value, considering that they're starting from the value of k is 1. One index is there. For example, here a tree is given to you. Now, this is very important to understand. Sometimes people get confused in this input and output of a tree as well in the comparative programming. So let me try to give you one important, inference about this input and output as well. At any point of time, whenever this kind of a input is given to you, let's say they will not give you the floated chart of a tree, and they will directly give you this kind of an input. So always remember, the input will be given in a way that you have to always start from a root node. So 3 is there, then you go to the left side. This is how the series will be forming. So you can create in your notebook as well, if you know, if you can understand the input how it is given. Then 4 is there, you have to create it towards the right. So you have to always create from the left side to the right side. Always the creation will happen from the left to the right. Okay. So you will always start from the root node and then keep on exploring towards left and then towards right. Then next value is null. So it means that once left is nothing, null is there, then once right is nothing but is 2. Okay. So this is a kind of a tree is given to you. This is a BST. I hope everyone agrees with me that this is a BST, right? This is a binary search tree. I hope everyone agrees with me. Is this valid or not? If you will observe, at every point of time, at every phase, left side contains the elements which is less than the parent value, right side contains the values which is bigger than the parent value. Now, what is they are asking? First smallest element. So what they're expecting as a result? The result that they're expecting is, in this scenario, is 1 itself. When the value of k is 2, answer will be 2. When the value of k will be 3, answer will be 3. When the value of k will be 4, answer will be 4. Now, in this case, what we will do, we will try to do the in-order traversal. This is what I will do the code part as well while doing the implementation. What we will do, we will do the in-order traversal. And afterwards, doing the in-order traversal, we will try to store it in one array. What we will be able to get, we will be able to get 1, 2, 3, and 4. And because it's an array, you all know that array will be stored as a zero-based indexing, right? So now if I want to get the value of k as 1, first smallest, so I need to extract the value of 0. So what I will do, I'll say what is the value of a result of k minus 1. So that will be the final answer which I will return. So far so good. Can we implement this code, this logic via code part? Everyone is ready? Shall I do the implementation if the logic is clear? Then maybe we will talk about the complexity part of the same. After that, once we will do the implementation, I'll talk about the complexity analysis for the same logic. Okay, we will discuss that part as well. Perfect. So let's get started and we'll do the implementation of the logic that we have discussed just now. So what is the first thing we have to do here? What is the first thing we have to do here? In order to find out the kth smallest element, the very first thing is I'll check it out, the base case condition. What is the base case condition that we have, right? So if let's say my root is none, if let's say my root is none, I hope my screen is properly visible to everyone, and even the text which I am writing here, it's visible, right? If let's say the root is none, in that case, I'll return directly, right? I'll return. that is not the case, then what we will do? We will try to create one result list, and then we will try to call the function which is in order traversal. Inside this, I will pass the root. So this is what where we have done something called as function calling, right? And this is something array to store the result of in order traversal. Fine. So here we have instantiated one list, or you can say list to store the results, and we have made the function calling as well. Okay. After this, what we should do in this particular method, finally, what is the last step? I want to return. What I want to return? I want to return what is the result value present inside k minus 1. Why k minus 1? Because I know that k minus 1 is the index number which will give me the value of a kth smallest element, right? Now the only thing which is left is to define the to make the function calling. To make the function calling, right? Sorry, not function calling, function definition. We need to define this function. So what we will do? Def in order traversal. Inside that, we will be having self and then node. Now, if let's say node dot left is not equal to none, what we supposed to do? You all know that in order traversal is composed of 3 steps. Step 1 is to traverse towards left subtree, right? So what we will do? We will say self dot in order traversal, and inside this you will call node dot left, right? What is the second step? What is the step number 2? Step number 2 is to store the elements inside the result array. So what we will do? We will try to say self dot res dot append. So these functions are there in Python to add the values in the result array. What is the third step? Third step is to traverse towards the right subtree. Now, if there is someone who really wants to do the implementation in Java or in C or in C++, please do it with me. Please do it with me. Open in your platform. Maybe I'll just try to share the link with you all in the comment section. And I really want you all to try just now on the live itself, right? So if you want to do it with any other programming language, please do it. Logic will remain same anyhow. Logic will not change, right? If node dot right is not equals to null, so what we will do? We will again call the function again. So in order traversal, and after that what we will do? We will say node dot right. Make sense? So these are the 3 steps which are required for the in order traversal. We are done. We have done that. Now let's try to maybe run this code first. So it is accepting, right? But as I always say that whenever you are trying to do any code on lead code, when you're running the code, it's not like that it's fine. It's just run for the 2 test cases. Until or unless you will not submit the code properly, it doesn't have 100% guarantee that your code is correct. So let me submit it as well, and then we will see that whether its submission is also happening properly. Yes, it is happening. So this is how, with the help of this logic, we will be easily able to find out the kth smallest element in a given binary search tree. Is this part is clear to everyone? Now you can do the same question here as well at your home to get the validation of a BST. The only logic which will get changed is, instead of returning this directly, you have to check it out that the result array which you will be able to get, whether the data inside that array is sorted or not. Is it sorted or not sorted? So how will you check that? It's quite simple. So let me do one thing. If let me just show you itself here itself. So the same thing will happen. Just instead of returning this, you have to make a small change. So everything above also will remain same. So you have to make the in order traversal in the above part. It will remain same. Now your result array will be filled with the sorted data. The only thing which will change now is you will say n is equals to, what is the value of n? N is equals to length of the result array that you have, self.res. Now what you will do, you have to check, you need to check whether the result list is sorted or not as per our logic, because just now we have discussed that if there is a valid BST, then definitely we will be able to get a ascending order sorted data. Acha, when I'm saying ascending order, then what I can do is maybe I can apply one loop for I in range n minus 1. And what I can do, I can compare the current element present in res of I. If let's say at any point of time, this current element which is present at ith index, it is bigger or let's say equal, because duplicacy is not allowed. If it is bigger or equal to the next element, self.res of I plus 1, at that point of time, what you will do? If that is the case, what you will do? You will return the answer as false. Because at this moment, I am pretty sure that the tree is not a valid BST. Because at any point of time, if this condition is true, it clearly indicates that my data is not at all sorted in a ascending manner. If let's say you will move out of this for loop and this condition will not get true at any point of time, then you will return the answer as true. It means that you will be able to get that valid binary search tree. That's it. That's the only change we have to do, right? The everything I have just copied from the previous code itself. The only thing, the only logic that I have changed is here. So if I just run this, let's see whether we will be able to get the correct result or not. It's accepted, right? If I just submit this, let's see. It is submitted. So simple, so easy. If you will just know the concept pretty well, implementation is just a cakewalk for us, right? So is this part is clear? So far, so good. Can I get some confirmation from everyone? Maybe by thumbs up, maybe by writing anywhere, whatever things you're comfortable with. So far, so good. Is this bit fast or is this comfortable with everyone? I'm speaking a bit fast because I want to cover up maximum out of this session with respect to the binary search tree. But if you will feel like that the speed is bit fast, you can tell me. I'll slow it down. If something is not clear, you can ask me. I'll repeat it again. Yes, yes, yes. Okay. Shall we move ahead then? Shall we move ahead? Yes or no? Perfect. Now we have done two amazing questions which are very frequently asked in interviews. Now let's talk about another problem as well, because I already have discussed that how the insertion is being done in a BST, right? How we can do the insertion in a binary search tree. So if I'll ask you, so here this is what they are asking, that given the root node and a value to insert, return the root node of a BST after the insertion. It is guaranteed that the new value does not exist in the original BST. So it is making sure that duplicacy is not there. So you don't need to worry about that. So here you can see that the input is this tree and the value is 5. Because the value is 5, so it will always start from the root node from 4. 5 is bigger than 4, so we'll go towards the right side. 7 is there. Now the value of 5 is smaller than 7, so we will go towards the left of 7 and we will be able to add that value, right? This is how basically we will be able to get the final output. Perfect. Now in terms of implementation, how we can do so? It's quite easy, quite simple. How? If let's say we will say root is none. Again, if my tree is empty, at that point of time, I need to create that new value as the root node, right? In that case, I'll return simply my tree node class that I have, and I'll try to insert that value inside that, right? Because if the root is none, it indicates that my tree is something. Uh, okay, John was saying, sorry, I just skipped the complexity part. We'll discuss. Just wait for a while. Maybe after this, because I have started now, we'll discuss after this. Okay, both the complexities we will discuss. So if the root is none, in that case, we can directly return it. Fine. Now, if that is not the case, in else part, what we can do, we have to just directly compare, because just now we have discussed, if let's say my parent value is smaller than the value that a user want to insert. This is the val which a user wants to insert. In that case, let me know whether we should move towards left or we should move towards right. If a user wants to insert a value which is bigger than the root value, parent value, at that point of time, should we move towards left or should we move towards right? Let me know what is the answer. Left or right? As per the properties that we have discussed in the very start of the session, what do you think? Where should we explore recursively? Left side or the right side? I hope everyone agrees with me that because the value is bigger, so we need to explore towards the right side. So what you will do, you will say root dot right and you will call the function recursively, insert into, what is the meaning of recursion? Calling the same method again, but with different set of parameters, that root dot right, because I want to go there, value will remain same. If that is not the case, it means the case is vice versa. The value is smaller than the root dot value. In that case, I have to move towards left. So I will again call the recursive function insert into BST. Here I will mention root dot left, comma, the val. So because of this condition, we will try to traverse towards right. And because of this condition, we need to traverse towards left, right? And finally, what we will do, once I will move out of this else part, we can directly return the root. Done. Let's run this code as well. Accepted. Let's try to submit this. It's done. Now, I hope this is again pretty much clear to everyone. Is there any doubt to anyone? Now, let's talk about the complexity part before jumping to any other further problem. In this case, we have talked about two problems in the very first two initial cases, implementation of two problems we have done. First problem is validation of a BST. Validation of a BST. And second problem is that we have talked about is kth smallest finding. In both of the problems, if you will observe, anyhow, we are using the same logic. We are doing the in-order traversal. We are storing that result in a result array. After that, in validation part, we are trying to make one more for loop to check whether the values are sorted or not. In kth smallest part, we are directly fetching the values of k minus 1. Okay. It means both of them are using in order. What is the complexity of in order traversal? Anyone who can let me know? Because in both of the cases, anyhow you are using in order traversal method. So how many of you knows the complexity of in order traversal? Can you tell me what is the time complexity required to do the in order traversal? Anyone who is having an idea? And let me know. So what we usually do in order traversal, we says that we are calling the recursive function in order. Then we explore towards the node dot left. If you remember that is the first step which I did in the code. After that, I tried to store my data, append that data, node dot val. And the third step which I did is, again, I call the recursive function again, but towards the node dot right. So these are the three steps which I have made, right? First, second, and third. So what is the complexity? Subhash is saying it's big of V plus E. Okay. How you get to know? Joan is saying N log N. Again, Vikas is saying it will be big of N. How you guys are getting the complexity? See, whenever we are talking about a binary search tree complexity part, and it is common for all the aspects which we will deal in BST, we usually have two different kinds of binary search tree. Please listen this thing, very important. It's very important to understand, and people get confused here. Whenever we're talking about BST, binary search tree, you will be dealing with a two different kinds of BST. One is something which is a balanced BST. Another one is something which is an imbalanced BST. Imbalanced BST. The example that we have just now discussed in the above part, this example, this example, this is a balanced binary search tree. Why is that so? What is the meaning of a balanced BST? The literal meaning is that you will be having equal distribution of left and right subtree. The number of nodes present in the left subtree will be almost equal to the number of nodes present in the right subtree. This is something that we call as a balanced distribution, right? Load is something is balanced in a binary search tree. So this is something which we call it as a balanced BST. Okay? So when I'm saying balanced BST, I hope you understood the point. I'm saying that when there is almost equal number of nodes, when there is almost equal number of nodes in a binary search tree, then you can say it as a balanced one. But if there is not that case, if there is not, or you can say there is unequal distribution, there is a unequal distribution of number of nodes, of number of nodes in left and right subtree. This is also I should mention in left, so that you will not get confused where I am referring these number of nodes. Left and right subtree. Then it is something which we call as imbalanced BST. Here also I should mention in left and right subtree. Almost equal number of nodes in left and right subtree. Okay. For example, if I'll give you one example of an imbalanced one, balanced one you already have seen. Let's talk an example of an imbalanced one. For example, if you will say 100 is there. So, okay, you have inserted 100 here. Let's say after that you will be having 70. You have inserted 70 here because 70 is smaller. Then let's say you will be having 50. You have inserted 50 here. Let's say you will be having 25. So you will insert 25 further here. Let's say you will be having then 110. You will insert 110 here. So in total, how many number of elements you have? 1, 2, 3, 4, 5. You will be having 5 elements. But almost more than half of your array is inclined towards the left side. And that's something which we call as a left skewed binary search tree. So all in all, we have two different components of a BST, balanced and imbalanced one. Now, if someone will ask you the complexity part, right? So it depends that if you are doing a in-order traversal in a balanced binary search tree, or you are doing a in-order traversal in an imbalanced binary search tree. So when you are doing a in-order traversal in a balanced BST, so what will happen? You are dividing your search space into two halves, T of n by 2 and T of n by 2, because you're calling it recursively. And this is a constant task. So your recurrence relation will be like T of n, which is equals to 2T n by 2 plus C. But when you're dealing with an imbalanced BST, then what will happen? Maybe more than half of your nodes, or almost all of your nodes except the root node, is available at the left side or is available at the right side. So your recurrence relation will become T of n minus 1 plus C. T of n minus 1 indicates that almost all the elements, n minus 1 elements, are either at the left side or at the right side. Plus a constant component is there. Now, if you will solve both of this recurrence relation, if anyone is not aware about how we can solve the recurrence relation, please go and check it out my video. I have created a very long video with respect to this part, that how there are various methods we have, mainly 3 methods: substitution, masters, and recursive tree. I have explained it already. So if you will solve it via those methods, you will be able to get in both of these cases, the complexity as big O of n. So all in all, doing this in order traversal is a big O of n task. So time complexity required in order to solve this above two codes is big O of n. Okay. Although you are using a new for loop also when you are talking about a validation BST. So big O of n plus big O of n is overall big O of n itself. So time complexity required for a validation BST code as well as finding out the kth smallest finding is also big O of n. When I'm talking about a space complexity part, what is the space complexity of this code? So space complexity says that how much extra space you are using to implement this code. Now I hope you remember that we are using extra space, which is a result array in both of them. Do you remember that? I have taken a list by the name of res to store my elements of the inner traversal. So that's why I have taken a size n list array. So space will also become big O of n. So time and space complexity is big O of n. Okay? Now, let's talk about the time complexity of insertion code that we have just now done. Again, in the insertion part, if you will observe, we are doing everything recursively, right? We will be having two things again. Either we are doing an insertion in the balanced BST or we are doing an insertion in an imbalanced BST. Now, when you're doing an insertion in a balanced BST, your recurrence relation will look like T of n, which is equals to T of n by 2 plus C. Here I am not mentioning 2. Please listen this statement very, very carefully because this is where you will get confused if you will not listen it properly. In the above scenario, when I was doing the in-order traversal, what is the recurrence relation I have mentioned? 2Tn by 2. Because when I'm doing a traversal, I have to move both left as well as right. But when I'm doing the insertion, I know that either I have to move towards left or right. I can't insert the element in both left and right. So if you remember the code part also, just now that we have discussed, in the insertion part, either I'm moving towards right part or I'm moving towards the left part. I can't go and explore both of the sides. I hope it makes sense to everyone. So that's why it is T of n by 2 plus C. And if you remember, this is the same recurrence relation that you usually have in binary search algorithm also, which we have in arrays. So the complexity will become log of n if you will solve this recurrence relation. If it's imbalanced, again, the recurrence relation will be T of n minus 1 plus C, which will come out to be big O of n. So all in all, your complexity in a binary search tree depends on the value, the height value. So in a generalized sense, if someone will ask you what is the complexity of insertion in a BST, you will say it will be big O of h. Now this h, which is the height of a BST, depends on whether my tree is a balanced tree or it's an imbalanced tree. If it's a balanced tree, it will be a logarithmic one. If it's an imbalanced tree, it will be a linear one. Even the same concept is applicable for the operations of searching as well as for the operations of deletion, which I think today I'll not cover up. Searching, I think you can do by your own. So I'll give you that as an assignment of today's session. Searching operation. So I'm just giving you the link of this question, and please try to do this question by your own, because now you know how you can do the searching. You know that whether if the element is present, if the element is smaller than the root value, you have to search towards the left search space. Otherwise, you have to search for the right search space, and that is the real application of BST. So until so far, we have understood what is BST, right? What are the properties of BST? But the question is also why BST is required, because it is really helpful in the searching operation. With the help of BST, if the tree is a balanced one, we will be able to optimize our complexity from big O of n in a normal tree to a log of n base 2, considering that we will be having something called as a balanced binary search tree. Then only answering this statement. Okay. So this is the application. This is the real-time application. So whenever we want our operation of searching, so we try to go for the BST thing. Okay. Apart from this, I don't know how many of you are aware about the concepts of database. In databases, we have a concept of file indexing in order to access any element faster, the files that we have. There again, BST plays a very important role. These are the real-time applications that we have with respect to the binary search tree. It's very, very crucial data structure. Even if anyone is from data science background, right? In a lot many clustering algorithms that we have, BST again plays a very important role in order to do the optimization part. Okay. So, in a nutshell, this BST plays a very important role. Yes, B plus trees are also there, which is really important for the file indexing per se. So, maybe I'll take a separate session altogether where I'll show you the importance of BST, B tree, B plus trees, all those stuffs. But that will be far low. In between, we need to go towards step by step. It's not like from first tier we can jump towards 10th tier. So today we have just talked about what is binary search tree, why it is required. We have solved two interview based problems: get smallest finding out, validation of a BST. We have talked about insertion, and one problem, that is the searching of a BST, I have given you as an assignment. Apart from this, I have talked about the complexity analysis, where I have talked about that how balanced versus imbalanced BST differs, and how it depends on the height value, and depending upon that your recurrence relation will get changed, and accordingly your complexity will get changed from logarithmic to the linear one. That's the overall concluding part of this today's session. It's been 1 hour that I am the only one who is speaking up. If you have any sort of doubt, you can ask from me. I'll conduct part two of this today's live, where the major prerequisite to have this part one to be done properly. Then, in the part two of the live, maybe I'll try to do it tomorrow itself, or maybe day after tomorrow. I'm not sure. I'll announce it on the on my LinkedIn. Please connect with me there, as well as on the community post of my YouTube channel as well. So in the part two, I'll try to talk about a deletion part, because deletion is a very bigger topic. It requires again another 1 hour for me to first of all explain you. Again, very important, very very important. And then we'll do the implementation. We'll talk about the complexity per se. So I hope that today's session you will be able to get the understanding that how we can do the insertion, and then maybe you will be able to do the searching on your own. Once you will be done with the searching part, I really want everyone to write the link of your GitHub code. So what you can do, once you will be able to write the code and you will be able to done that, you can upload it in your GitHub profile, so that you can also refer in your future as well. Okay. Then just copy that URL in my comment section of this video and let me know that here is my code of searching a element in a BST. So I'll check it out whether your code is correct or not, synthetically and logically, and will in the same thread I'll respond to you that yes, it's perfect, or it's not logically perfect. Okay. So do try to do the assignment as well, because until and unless you will not write your own code, and it doesn't matter that how many number of videos you will watch. As I always say, that practice is the important point here. Once you understood the concept, please do a lot of practice. Okay. Now, if you have any sort of doubt, anything, any question you want to ask, I am here for the next 5 minutes. We'll try to answer all your questions. If you want to give any sort of feedback, how is this session, today's session, whether you will be able to learn everything or not, you can also give that. I'm open to take any sort of feedback, whether it's positive or negative, right? Please explain Dijkstra's Bellman Prim's implementation in your upcoming videos. Is this not there in my playlist? Okay, if it is not there in my playlist, then I'll definitely make this also live session. Um, yeah, it's not there. Even greedy algorithm itself is not there. I can't see. So yes, we can do a live of this part as well, Subhash. Definitely we will do. So what I'm doing is I am planning to make it in a more advanced level, this playlist itself. So whatever videos, whatever live I will take, I'll keep on adding the videos there itself, because as of now, this playlist is from basic to intermediate level. Now I think it's the right time that we will move towards intermediate to advanced level. So whatever topics are pending in this complete DSA full-fledged playlist, I'll keep on taking the live and adding that videos in this playlist itself. So that after some point of time, it will be very mature, And if anyone wants to check it out, anyone wants to learn DSA from a scratch, from a beginner level, they will be able to understand. If they follow everything from a series part, they will be definitely able to get the understanding. So that's my future plan, right? Definitely we will do, not an issue. But as of now, because we have started BST, let's try to complete that first. And then maybe after going forward, we will try to pick up the greedy algorithm module. There, maybe we will cover up all these things. Okay. From where you have learned maths and data structure, your concepts are really, really very, very good. I have learned by my own, no as such course, nothing like that. But yeah, I have spent a lot much time in learning these videos. As I always refer, MIT lectures are there. If you go and check it out on YouTube, it's freely available. I have learned a lot from those videos. It's a very standard YouTube videos with respect to DSA, which I always recommend to everyone. Apart from this, Corman is the book, which is a standard book. Even you will find the ebook on my GitHub ID. That book is also very amazing. I have learned from that book as also. So these two are the resources of my learning. If you go and check it out, it's freely available. You can go and explore these resources. You will be also able to learn that. The only thing is, the only pain point is that you have to spend your own time there. If you don't have, obviously mentor will help you out. But if you have the time, then do spend. You will be definitely able to get these concepts pretty well, right? Actually, I completed your course of DSA. You are my inspiration, but can't understand the graph algorithms except that I learn everything. Definitely, if it's not there, maybe I'm not sure. But in this playlist, definitely that's my real target. I want every video of DSA should be there in this playlist. Not a single video should be pending. In the upcoming few months, definitely this playlist will also get very, very matured. So whatever topics are pending, if you feel like that apart from this also there are few topics which are pending in this playlist, please mention in the comment section. Definitely I'll take it each and every section, live sessions. I'll come live, explain to you, do the live implementation, so that we will be able to get a proper things to be done in a proper appropriate manner, and everyone will be able to learn out of this. This is what the ultimate target of this YouTube channel, and that is what I really want to achieve. Please do share these videos with everyone, these playlists with everyone. Still there are so many people who are really not aware about this channel. The reach is not that much huge until so far. So I really want you guys to please support this channel towards sharing with your friends, uh, with your colleagues, whosoever is looking for this kind of a knowledge, right? And I think with this, let's end today's live. I hope you find today's live insightful, and I'll see you all very soon in the upcoming live, where now we will do the part 2 of this BST session, where we will specifically discuss about the deletion part. Okay. Do subscribe, do like the video, right, if you really find it insightful, and do mention the code part of a searching in a BST. Is it MIT open course where you were talking about? Maybe I can share you a link of which I am talking about, the playlist. So you can just check it out, MIT data structure and algorithms. You will be able to find the link also. Even I have also shared, so you can check it out. Okay, very amazing. But yeah, you have to spend your own time. In the first go, maybe you will not able to understand, but definitely if you will take it step by step, you will be able to understand. Always remember that whenever you are learning something new, this is what I always do. It's not like that I know everything. I am also in a learning phase, whether it's be a concept of DSA or any other beat in any other domain. I always learn from the standard resources, even if I learn from any video. Okay, so I always mention, check, step back towards the documentation and do my own research. No one consider no one it as an idol. Okay, so even not me, someone if is saying that you are my idol, you know everything, I'm learning from you, I will definitely say please don't rely 100% on any of the mentor. Maybe he or she can speak something wrong as per her or his experience. Always take your self research also. Always try to spend your time on self learning also. This is what the advice which I always give whenever I meet physically or virtually to any of the students. Because nowadays, what I'm observing is that people are completely relying on their mentors for learning per se. It's good that you will be easily able to understand the concepts from the mentors. That's completely fine. But after that, please mention, do your own research, explore by your own. If you're not doing your own self research, then obviously whatever knowledge your mentor is having, that much you will be having. But if you want to explore more things around you, then obviously you have to spend your own time on top of that. Okay, so always remember that self learning is very very important. From wherever you are learning, I don't care whatever videos you are watching, I don't care whatever course you are buying, I don't care. But on top of that, if you're not doing any self learning, then everything will go in vain, because then you're restricted. There is a black box which is there, and you're not going out of that box. If you want to go and explore more stuffs in that domain, you have to spend your own time. Okay? That's what I really do on my person. That's what I'm sharing with you all. Whatever things I'm doing, I'm sharing with you all, and that will really help you in order to grab the concepts pretty well, and then everyone will appreciate those concepts just like the way you're doing for me. Then everyone will do for you also, right? So thank you so much, Vikas Kumar, for joining in. Thanks, it will be helpful. Thank you so much. Love the session. Thank you so much. Hope to see you soon. Yes, very definite. Very soon we will do it live. I'll just post it in the community as well as in the LinkedIn post. Bye bye, everyone. See ya. Take care. Good night. Right? Bye bye.